me a 1 in the chat if you got your notes ready, and we will get started. This one, again, is going to be pretty calculator heavy. So we're going to talk about least squares, regressions, and residuals today. So a least squares regression is a line of best fit. And it's just a specific way to calculate a line of best fit. And it's the one we use in AP Statistic. It's probably the most popular way to create a line of best fit for a scatter plot. All right, so you'll want to get down what's in the green box. And it's just talking about what a regression line is. And all a regression line is a model for the data, much like a density curve. So it's a line that describes how a response variable y changes and as an explanatory variable x changes. And we can use it to make predictions for the output y for given values of x. And so that little example there is we got a scatter plot of the mileage on used cars and the price that they sell for. And so the regression line would help us predict the price you could sell a car for given the miles that it has been driven. All right, so I'll go ahead and wait for you to get this down. And just give me a 1 in the chat again when you're ready to go. You don't have to write all this down verbatim, but what you will want to write down is the regression model that we use here. So it has the form y hat equals a plus bx. Y hat is a predicted value of the response variable y for a given value of the explanatory variable x. It is actually read as y hat. The little caret is called a hat. And the hat just means it's a predicted value. It's not an actual y value from our data set. It's a predicted value from our regression line. And this is really just slope-intercept form of a line, right? So b is the slope, which is the amount by which y is predicted to change when x increases by 1 unit. That's important when you're trying to interpret the regression line, but we'll get that. And a is the y-intercept, which is the predicted value of y when x is 0. All right, it's too hard seeing a bunch of 1s. Give me a 2 this time when you're ready to move on, so that'll kind of change it in my chat. Great. All right, let's do an example here. So this is an example where 2 AP Statistics students wanted to investigate if tapping on a soda can reduces the amount of soda that sprays out. You guys do that? I feel like it's a very Midwest thing to do. You tap the can before you open it. So they shook up a bunch of cans, and then they randomly assigned each can to be tapped for either 0 seconds, 4 seconds, 8 seconds, or 12 seconds. And then after they opened them, they measured the amount of soda that was left in each can. All right, so what we want to do is create a scatter plot and a least squares regression for the following data. And I want to take a second before we do this. I want to talk about why it's called a least squares regression. And normally in class, I have kind of a cool diagram or an interactive one that I would use. And maybe I'll show it to you guys next time. I think, like I said, this is going to probably take 2 classes to get through. But here's the reason it's called a least squares regression. The actual way it's created is using calculus. So if you were a calculus student of mine, you'll understand some of the terms. If you weren't, don't worry. I'll be able to explain it in a way, hopefully, that you can understand. So The way that the regression line is created is we're going to find out that this distance, the vertical distance between any single data point and the regression line, that's called a residual. So what you do is you find all those vertical distances and you square them, right? And that's going to give you an area, and you total up those areas. So you total up the areas of all those squares. And what you do is you use calculus to optimize. So you guys that were in calculus, remember optimization problems where you find a maximum or a minimum? And so you find the line that optimizes that area, meaning that minimizes the total area of those residuals squared. So it's the line that gives you the least amount of area in these squares. It makes it the smallest, and that's why it's called a least squares regression line. Does that make sense? So it's the line that gives you the minimal area in all of these squares. Any other line would have a larger total area. Anyways, that's why it's called a least squares regression or an LSR. So how we want to enter this into our calculator, our explanatory variable is the time. So the tap time. And our response variable is the soda remaining, right? So the way we want to enter this is in list 1, we're going to enter the tapping time. You're going to have to enter 10 zeros, 10 4s, 10 8s, and 10 12s. Does that make sense? And then corresponding to that, you'll enter the tap time. So I'll go ahead and do that. You can kind of follow along. All right, and then we want to enter the corresponding soda remaining. All right, so I got all my data entered. I'm going to do second. Stat plot, make sure that you're graphing the data in the correct lists. I'll do a zoom 9. There we go. There's our data set, right? Clearly a positive association. So now I'm going to teach you guys how to do a regression. I kind of went over this last time. It's the same way we find the correlation, right? So we're going to go to stat and then calc, and it's this lin-reg. Now, just to be consistent, they give you 2 options for lin-reg. They give you the 4th option there and the 8th option. And the one that we have in our notes, it's in the form of that 8th option, right? It's the A plus BX form. And it doesn't matter. They're the same thing. It's just in the 4th option, A would be the slope and B would be the y-intercept. But in the 8th option, it's written in the form that we took in our notes. So we might as well use that one, right? So choose the 8th option. Make sure you tell it the correct lists. So list 1, list 2, Frequency list, you'll leave blank. Now, store regression equation. We do want to do that this time. We're going to tell it to store it in Y1. And that way it'll graph the regression line right over our data for us. So you can find Y1 in vars, yvars, function, and there it is. It's kind of buried pretty deep in there. And then I'll hit calculate. Now, some of you might have an older operating system, so you don't get this menu, and I'll tell you what the syntax is in that case. In the case that you don't have that menu, the syntax would be this. You would choose that linreg option, and then you would just do L1, L2, Y1. And the comma is right above the 7. So it's explanatory variable, comma, response variable, comma, where do you want us to store the regression equation? Does that make sense? And then when you hit enter, you should be able to see a couple of things. It'll tell you, okay, here's the form I'm giving you the regression equation in. And then it'll tell you, here's what A is. So this is my Y-intercept, 248.64. Here's your slope. It tells you what R squared is. We'll talk about what that means in a couple sections. And then here's your correlation. So pretty high correlation, right? Strong positive, 0.92. Now if you go into Y equals, you'll see that it put that regression equation in there for us. And if you graph it, boom, there's your regression. Any questions? Is everybody able to get this? That's what I'm most concerned with. I want you to be able to get this in your calculator. Yeah, I will. So, Maya, do you have is your calculator the menu type or the one where you have to enter it this way? Okay, so you have, when you go to regression, you get the menu. So, store regression equation. There's a shortcut. I'll show you the shortcut. So it's in vars. You go vars, then yvars, then function, then y1. But there's a shortcut. If you click alpha, then trace, that also just immediately brings up your y variables. Everybody good? Sam, you good? Okay. Riley? Both Rileys are good. Grace, you good? Awesome. Great. So there's our regression. All right, so let's answer some questions about this. So it says, interpret the slope and y-intercept of the regression line. So if you go back into your calculator, you can look at your slope. Our slope was 2.635. So always think of your slope as a fraction, right? So it's our slope is 2.635 over 1. And what you want to think about is what your explanatory and response variables were, right? So if we think about this on an xy axis, our explanatory was tap time. Right? And our response was soda remaining. And it was in milliliters. And tap time was in seconds, right? And remember that a slope is always rise over run. So if you think of that in terms of units, that's milliliters of soda remaining over seconds of tap time, right? All right, so when we interpret the slope, that's kind of how we want to interpret it, right? The 2.635 is milliliters of soda remaining. And the run, which is horizontal, is seconds of tap time. And remember that the regression line is for making predictions. So you have to use that verbiage when you describe the slope. So we're going to say, and it's a positive slope. So I'm going to say this: there is a predicted increase of 2.635 milliliters of soda remaining for every additional second of tap time. Does that make sense? If it were negative, then you would say there's a predicted decrease of 2.635 milliliters of soda remaining for every additional second of tap time. Since it's positive, we say there's a predicted increase. Got to use that word predicted. If you just say there is an increase, you're going to be marked down for that, because the regression line is for making predictions. It's not true data, right? Okay, the Y-intercept. What was our Y-intercept? It was 248.64. And so the Y-intercept is when your X value is 0, right? If we go back here, whatever the Y-intercept is, it's when your X value is 0. So the way we would want to state that is that for a tap time of 0 seconds, we predict 248.64 milliliters of soda remaining. Good?